Here's something that might surprise you. When you search Google for running shoes, it also finds results about jogging sneakers. But if you ran that same query against a traditional database, a SQL where clause, a keyword match, you'd get nothing. Because the word running doesn't appear in jogging, and shoes isn't sneakers. The database doesn't know they mean the same thing. It doesn't understand meaning at all. Vector databases do, and they've quietly become one of the most important pieces of infrastructure in modern AI. If you've used ChatGPT with your own data, searched Spotify for a podcast by describing what it's about, or gotten eerily good product recommendations, there's a vector database behind that. By the end of this video, you'll understand exactly how they work, why they exist, and when you should and shouldn't use one. Let's start with why traditional databases fall short. SQL databases are brilliant at structured queries. Give me all orders where the price is under $50 and the status is shipped. Boom! A B-tree index handles that in microseconds. But what happens when your data is a paragraph of text, an image, an audio clip? You can store it, sure, but you can't search it by meaning. Full-text search engines like Elasticsearch help. They tokenize words and match on term frequency, but they're still fundamentally matching strings. Search a wine catalog for wine for seafood and you'll miss a wine described as pairs well with fish, because the literal word seafood doesn't appear. And this matters more than ever. The overwhelming majority of data being generated today is unstructured. Text, images, audio, video. Traditional databases were never designed to understand what that data means. They compare values, they don't compare concepts. That's the gap a vector database fills. So here's the core idea. What if you could convert any piece of data, a sentence, an image, even a code snippet, into a list of numbers that captures its meaning? That's exactly what an embedding model does. You take a sentence like the best coffee shops in Amsterdam and run it through a neural network, something like OpenAI's text embedding model. Out the other end comes an array of, say, 1536 floating point numbers. That array is a vector, and its position in this high-dimensional space represents the meaning of your input. Think of it like the RGB color model. In RGB, every color is a point in a three-dimensional space: red, green, blue. A vector database scales that same idea to thousands of dimensions. Instead of color intensity, those dimensions represent abstract semantic features. And here's the magic. Things that mean similar things end up close together. Coffee shops in Amsterdam and cafes in the Netherlands would land near each other. How to fix a Python import error would be far away. A vector database stores millions, sometimes billions of these points and lets you ask one simple question. What's closest to this? But here's where it gets interesting. Finding the closest point sounds simple, but computing the distance between your query and every single stored vector is a 0-n operation. At a million vectors, that might take 10 milliseconds. At a billion, way too slow. So vector databases use approximate nearest neighbor algorithms, ANN. They sacrifice a tiny bit of accuracy for massive speed gains. The industry standard is called HNSW, Hierarchical Navigable Small World. Think of it like a multi-level highway system. The top layer has just a few nodes connected by long-range links, like interstate highways that get you across the country fast. Each layer down gets denser and more local. State roads, then city streets, then individual blocks. When a query comes in, you start at the top, hop to the general area fast, then drill down through the layers to find your exact neighborhood. The result? Logarithmic search time, sub-millisecond queries, at 95% recall or higher. There are other algorithms. IVF partitions space into clusters, product quantization compresses vectors to save memory, disk-n moves the index to SSDs for datasets that won't fit in RAM, but HNSW is the backbone of most production systems today. So the full pipeline looks like this. First, your application generates an embedding using the same model you used when inserting data. And that's critical, the same model. Then, the vector database runs ANN search to find the top k nearest neighbors. Then, it optionally applies metadata filters. Only show me results the user has permission to see or only from the last 30 days. Then it returns results with similarity scores. That metadata filtering step, it's actually one of the hardest engineering problems in this space. Do you filter before the search and risk breaking the graph navigation? Or after and risk getting back 0 results? The best systems, Qdrant, Pinecone, integrate filtering directly into the graph traversal itself. So who's actually using these in production? Spotify uses vector search for podcast discovery. They encode episodes and queries into a shared embedding space, index them in Vespa, and fuse the semantic results with keyword matches from Elasticsearch. So when you search electric cars climate impact, you find an episode titled EVs and the Environment. Perplexity, the AI search engine with over 15 million monthly users, built its entire retrieval layer on vector search. It chunks web pages, embeds them, and retrieves the most relevant passages to ground its LLM responses in real data. Sub-100 millisecond latency. Billions of documents. Airbnb uses embedding-based retrieval trained with contrastive learning, pairing booked listings against rejected ones, to handle complex queries like flexible date searches across entire countries. The vector search rapidly narrows millions of listings to a relevant candidate pool. And then there's the biggest use case of all, RAG, Retrieval Augmented Generation. Almost every company building LLM-powered products is storing chunks of their knowledge base as embeddings and retrieving them at query time to ground the model's responses in facts. That's a vector database doing the heavy lifting. The ecosystem breaks into a few categories. Purpose-built vector databases like Pinecone, fully managed, zero ops but closed source. Milvus, open source, cloud native, built for billion-scale workloads. Weaviate, strong on hybrid search, open source. Qdrant, built in Rust, exceptional at fast metadata filtering. And Chroma, lightweight, perfect for prototyping. Then there are vector-extended traditional databases. pgvector adds vector search to PostgreSQL. And honestly, if you're under 10 million vectors and already using Postgres, this might be all you need. Elasticsearch added ANN in version 8. Redis has in-memory vector search that's sub-millisecond. Even Oracle is embedding ML runtimes directly in their database engine. And then there's FAISS, Meta's open source library. It's the engine behind many of these systems, but it's a library, not a database. No persistence, no replication, no real-time updates, great for research and batch pipelines, not a production service on its own. Now here's where I need to be honest with you. Vector databases are not magic relevance machines. The number one misconception? That the database understands language. It doesn't. The database does geometry. The embedding model determines what close means. If your model is bad, your results are bad, regardless of how good your database is. Second, vector search does not replace keyword search. When you need exact matches, product SKUs, legal terms, diagnosis codes, BM25 crushes vector search. That's why hybrid search combining both is becoming the standard. Third, approximate means approximate. At 95% recall, you're still missing 5% of true matches. That's fine for recommendations. It's a real problem for compliance. And fourth, this stuff is expensive. 1 billion vectors at 1536 dimensions is about 6 terabytes just for the raw vectors, before index overhead. Keeping HNSW graphs in RAM multiplies that cost further. So when should you use something else? If you're under 100,000 vectors, a brute force search in NumPy works fine. Under 10 million, pgvector is probably enough. If your workload is primarily exact match, or you need strong ACID transactions, stick with your relational database. Here's the big picture. Vector databases solved a fundamental gap. How do you search by meaning instead of matching strings? They convert concepts into coordinates and retrieval becomes geometry. That's the mental model. And the trend is clear. Vectors are becoming a data type, not a separate database category. Every major database is adding native vector support. The question isn't whether you'll use vector search, it's whether you'll need a purpose-built system or whether your existing database will handle it. If you want to see how vector databases stack up against each other in a head-to-head comparison, let me know in the comments. And if this helped you finally get what vector databases actually are, hit subscribe. I'll see you in the next one.